What if two particles, separated by the entire universe, could still behave as if they are one system, not connected by a signal, not linked by a force, but joined by something deeper, a shared physical reality? This is quantum entanglement. When Albert Einstein first encountered this idea, he rejected it. He called it spooky action at a distance. He believed no influence could travel faster than light. And yet today, entanglement is not only accepted, it is experimentally confirmed and actively used in emerging technologies. But it raises a question that still challenges physics. How can two objects remain connected across space without any visible connection? To answer that, we need to go back to the foundations of quantum theory. In the 1920s, a new theory was emerging: quantum mechanics. Scientists like Niels Bohr and Werner Heisenberg were discovering that atoms do not behave like classical objects. Instead, they exist in states of probability. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper known as the EPR paradox. They argued that quantum mechanics must be incomplete because it predicted something strange. Two particles could become linked in such a way that measuring one instantly determined the state of the other, even across large distances. Erwin Schrödinger, who helped develop quantum theory, gave this phenomenon the name entanglement. For decades, it remained a philosophical debate. No experiment could definitively test whether it was real. That changed in the 1960s. In 1964, physicist John Bell developed a mathematical test. John Bell showed that no theory based on local hidden variables could reproduce all predictions of quantum mechanics. He created what are now called Bell inequalities. These inequalities gave scientists a way to test whether reality is locally realistic, objects have definite properties, no instant influence, or fundamentally non-local, quantum entanglement is real. For the first time, the question became experimentally testable. In the 1970s and 1980s, experiments began testing Bell's predictions. One of the most important was performed by Alain Aspect in 1982. Alain Aspect measured entangled photons and found results that violated Bell's inequalities. This was a turning point in physics. It showed that nature does not obey local realism. Later experiments improved precision and closed major loopholes. In 2015, multiple independent teams performed the loophole-free tests of Bell's theorem, closing decades-old experimental loopholes and strongly confirming quantum entanglement. These experiments demonstrated that entangled particles remain correlated even when separated by large distances, without any classical signal between them. But how do scientists actually create entanglement? It does not happen randomly in everyday objects. Instead, it is carefully engineered in laboratories. One common method uses light particles, photons. A high-energy photon is sent into a special nonlinear crystal. Inside the crystal, it splits into two lower-energy photons. But these photons are not independent. They are created in a single shared quantum state, entangled. In this state, measuring one photon instantly defines the result of the other, but neither has a definite property before measurement. Entanglement can also be created in trapped ions, electrons, superconducting circuits, ultra-cold atomic systems. These experiments require extreme conditions, near absolute zero temperatures, isolation from vibration, and heat vacuum environments, because entanglement is extremely fragile. Even tiny interactions with the environment destroy it, a process called decoherence. Entanglement does not allow faster-than-light communication. This is a critical point. Although measurement outcomes are correlated instantly, the results themselves are random, So no usable information can be transmitted. Instead, entanglement means that quantum systems are described by a single shared state, even when separated in space. It is not a signal, it is a relationship encoded in the mathematics of quantum mechanics. Today, entanglement is no longer just theoretical, it is the foundation of emerging technologies. Quantum cryptography uses entangled particles to create secure communication systems. If someone tries to intercept the transmission, the quantum state changes, revealing the intrusion. This makes communication theoretically tamper-evident. Quantum computing uses entangled qubits to perform calculations in parallel states. This enables new approaches to problems that are extremely difficult for classical computers. Entanglement has been demonstrated over long distances, including satellite-based experiments. In 2017, China's Maisha satellite distributed entangled photons over more than 1,200 kilometers. This is a major step toward a future quantum internet. Entanglement also enables quantum teleportation, the transfer of quantum state information from one particle to another. This does not move matter, but it transfers the exact quantum state. Conclusion: what it means for reality. Quantum entanglement reveals something profound. The universe is not built from isolated objects. It is built from relationships. Even across vast distances, nature maintains connections that classical physics cannot explain. We can use entanglement, we can measure it, we can engineer it, but we still do not fully understand why it exists. And that remains one of the deepest mysteries in modern physics.